Welcome all to the course of Data Communication and Networking, B7 semester Electronics and Communication Engineering. We are discussing Unit 4 called as a Medium Access Layer, and our topic is Multiple Access. Today's topic for the discussion is CSMA CA, CSMA CD and a CSMA. Up to now we have discussed an Aloha protocol. We start our discussion with CSMA, means Carrier Sense Multiple Access. In our Carrier Sense multiple access, to minimize the chances of the collision and therefore the increase of the performance, our CSMA method was developed. So it is the main motto to develop a Carrier Sense multiple access. A chance of collision can be reduced if a station senses the medium before trying to use it. So our Carrier Sense multiple access requires that each station first listen to the medium or checks the state of the medium before the sending. In other words, CSMA is based on the principle of a sense before the transmit or listen before the talk. CSMA can reduce the possibilities of the collision, but it cannot eliminate it. The reason for this shown is figure over here. A space and the time model of a CSMA network. Fine. The stations are connected to the shared channel, usually a dedicated medium. The possibilities of the collision still exist because the propagation delay between when a station sends a frame, it still takes a time or very short for the first bit to reach its destination, or any station for every station to it to send. In other words, a station may sense the medium and find it ideal only because the first bit sent by the another station has not yet been received. Anytime T1 station over here, our station B sense the medium and find it is ideal, so it sends the frame. At a time T2 over here, T2 is greater than T1, a station C senses the medium and finds it is ideal because at this time the first bit from the station B have not reached the station C, and our station C also send a frame. The two signals collide and both frames are destroyed. Fine. Our CSMA protocol also have a vulnerable time. So let's discuss a vulnerable time. The vulnerable time for the CSMA is a propagation time TP. This is the time needed for the signal to propagate from the one end medium to the another. When a station sends a frame or any other station tries to send during this time, a collision will be result. But if the first bit of the frame reaches to the end of the medium, every station will already have heard that the bit will remain from the sending. Our figure shows a worst case when the leftmost station A sends a frame at a T1 which reaches the rightmost station D at the time T plus TP. The gray area shows a vulnerable area in the time and space. Fine. So this is a vulnerable time or propagation time. A persistence method. Why we use it? What should a station do if a channel is busy? What should a station do if the channel is ideal? Three methods have been devised to answer this question. First, a one persistent method, the non-persistence method, and a p-persistence method. Our figure shows three of these methods by this figure, and behavior of this three persistence method when a station find a channel is busy. In the first persistence method, it is simple and straightforward. In this method, after the station find a line ideal, it sends the frame immediately with probability of 1. This method has a highest chance of collision because two or more stations may find the line ideal and send their frame immediately. Second, a non-persistence method. In this method, a station that has a frame to sends the line. If the line is ideal, it sends immediately. If the line is not ideal, it waits for a random amount of time, then it sends the line again. A non-persistence approach reduces the chance of collision because it is likely that the two or more stations will wait the same amount of time and retry to resend simultaneously. However, this method reduces the efficiency of the network because the medium remains ideal when there may be a station with a frames to be sent. Last, a p-persistence method. It is used if a channel has a time slot with a slot duration equal to or greater than the maximum propagation time. Fine. A p-persistence method combines the advantage of the other two strategies. It includes a chance of collision, also reduces by this, and improves efficiency. In this method, after the station finds that the line is ideal, it following some steps as mentioned over here. First, with a probability of a p, a station sends its frame. Second, with a probability of q is equal to 1 minus p, the station waits for the beginning of the next slot and checks the line again. So it is a flow chart of our three method. So in the third, if the line is ideal, it goes to the step 1, and if the line is busy, it acts through the collision has occurred and use the back to the procedure. Fine. So it is our CSMA protocol for our channel. Now a CSMA CD means carrier sends multiple access with collision detection. The CSMA method does not specify the procedure of following a collision. A carrier sends multiple access with collision detection arguments that the algorithm is handle a collision. In this method, a station monitors the medium after it sends a frame to see if the transmission was successful. If so, the station is finished. If, however, there is a collision, the frame is sent again. To better understand the CSMA CD, let us look the first bit of transmitted by the two stations involved in the collision. Although each station contains or continues to send bits in the frame until it detects a collision. We saw that what happens at the first bit in the collide. In our figure, a station A and station C are involved in the collision. At the time t1, a station A has executed its resistance procedure and starts sending its bits from its frame. At a time t2, over here, at a time t2, a station C has not yet sensed the first bit of sense by the A. A station C executes its resistance procedure and starts sending the bits in its frame, which propagate both to the left and to the right. The collision occurs sometimes after the time t2. Our station C detects a collision at a time t3. When it receives the first bit of the A frame, our station C immediately or after the short time aborts the transmission. Our station A detects the collision at a time t4 over here. When it receives the first bit of the C's frames, it is also immediately aborts the transmission. Looking at the figure, we see that A transmit for the duration of t4 minus t1 in this duration, and C transmit the duration of t2 minus t3 or t3 minus t2. Later we saw that for the protocol to work, the length of any frame divided by the bits rates is the protocol must be more than either of this duration. At a time t4, the transmission of the A's frame, though incomplete, is aborted. At a time t3, the transmission of B's frame, although incomplete, and is aborted. Note that we know that the time duration for the true transmission, we can show a more complete graph in our next figure. So in this figure, it is a minimum size frame size are there. For the CSMA CD to work, we need a restriction of a frame size. Before sending the last bit of the frame, our sending station must detect a collision. If any of this and abort the transmission, this is so because our station, once the entire frame is sent, does not keep a copy of the frame and does not monitor the line of the collision detection. Therefore, our frame transmission time TFR must be at least 2 times of the maximum propagation time TP. To understand the reason, let us think about a worst case scenario. If a 2 station involved in a collision are maximum in the distance apart, the signal from the first takes time TP to reach the second, and the effect of the collision takes another time TP to reach the first. So our requirement is that the first station must still be transmitting after a 2 TP. So let's have an example. It will example for our minimum frame size. A network using a CSMA CD has a bandwidth of 10 Mbps if a maximum propagation time, including the delays in the devices and ignoring the time needed to send the jamming signal, we will say later, is 25.6 microsecond. What is the minimum size of a frame? So the minimum frame size or transmission time TFR is equal to 2 times of TP is 51.2 microsecond. This means that in worst case, a station needs to transmit a period of 51.2 microseconds to detect the collision. The minimum size of the frame will be 10 Mbps into 51.2 microsecond is equal to 512 bits or 64 bytes. This is actually a minimum size of the frame of the standard Ethernet. Okay. So what is the procedure for our CSMA CD? With the help of the flow diagram or flow chart, let's discuss the procedure of our CSMA CD. It is similar to the one of the Aloha procedure or Aloha protocol, but there is some difference in the procedure. The first difference is in addition of the persistence process. Fine. So persistence process is added over here. We need to sense a channel before we start the sending the frame by using one of the persistence method we have discussed previously, a non-persistence method, first persistence method, or p-persistence method. The corresponding box can be replaced by one of the persistence method in our figure number 11, which is discussed for our Aloha. Our second difference in our frame transmission. In Aloha, we first transmit the entire frame and then wait for an acknowledgement. In our CSMA CD, the transmission and the collision detection is a continuous process. We do not send the entire frame and then look for the collision. The station transmits and receives continuously and simultaneously using the two different ports. We use a loop to show that over here the transmission is continuous process. We constantly monitor in our order to detect one of the two conditions, either transmission is finished or collision is detected. Fine. Either even stops the transmission. When we come out the loop, if a collision has not been detected, it means that the transmission is completed. Fine. So it will success our frame. Otherwise, the collision has occurred. Fine. The third difference in the sending of a short jamming signal that enforces the collision in the case that the station have not yet sensed the collision. So the jamming signal will be there. So it is a flow chart of our CSMA CD. So let's discuss the energy level for our CSMA CD. We can say that the level of the energy in the channel can have three values: 0, normal and abnormal. At our 0 level, a channel is ideal. At a normal level, a station has successfully captured the channel and it is sending a frame. At an abnormal level, there is a collision and the level of the energy is twice than the normal level. So at this stage, it is our ideal channel, it is a frame transmission, it is our normal, and it is our abnormal stage, means collision is there. A station that has an frame to send or is sending a frame needs to monitor the energy levels to determine if the channel is ideal, busy, or in collision mode. Fine. Our figure clearly explains these three situations: transmission, idealness, and collision. Fine. So what is the throughput of our CSMA CD? The throughput of our CSMA CD is greater than the pure or slotted Aloha. The maximum throughput occurs at the different value of the G and is based on the persistence method, the value of a P in the P persistence method. For a 1 persistence method, the maximum throughput is around 50% when G is equal to 1. For the non-persistence method, the maximum throughput can go up to 90% when G is between 3 to 8. Means our throughput of our CSMA CD will higher than the throughput of our Aloha. Fine. So it is the CSMA CD. Now let's go for a CSMA CA. CSMA CA is the carrier sense multiple access with collision avoidance. The basic idea behind our CSMA CD is that the station needs to be able to receive while transmitting to detect the collision. When there is no collision, the station receives one signal in its O signal. When there is a collision, the station receives two signals, its on signal and the signal transmitted by the second station. To distinguish between these two cases, our receiver signals is two cases must be significantly different from each other. In other words, the signal from the second station needs to add a significant amount of energy to one created by the first station. Means there is an energy difference between two signals. In our wire network, the received signal has almost the same energy as the signal because the either length of the cable is short or there is an repeaters that amplify the energy between the sender and the receiver. This means that in a collision, the detected energy almost doubles. However, in our wireless network, much of the sent energy is lost in the transmission. Our received signal has very little energy. Therefore, a collision may add only 5 to 10% additional energy, which is not useful for an effective channel collision detection. We need to avoid the collision on the wireless network because they cannot be detected. Carrier shunt multiple access within collision avoidance was invented for this network. Our collisions are avoided through the use of CSMA three strategies: interframe space, contention window, and the acknowledgement, which is shown in this figure. So there are three strategies used in our CSMA is contention window, our send frame, our interframe space, and our acknowledgement. Fine. So let's discuss this figure. First is IFS. IFS means interframe space. A first collision are avoided by the deferring the transmission even if the channel is found ideal. When an ideal channel is found, a station does not send immediately. It waits for a period of time called as an interframe space, this time IFS. Even though the channel may appear ideal when it is sensed, the distant station may have already started transmitting. The distant station's signal has not yet reached this station. The IFS time allows the front of the transmitted signal by the distant station to reach this station. If after the IFS time the channel is still ideal, the station can send, but it still needs to wait a time equal to the contention time. The IFS variables can also be used to prioritize our station or frame types. For example, a station that is assigned a shorter IFS has a higher priority. So we can say that in our CSMA, an IFS can also be used to define the priority of the station or a frame. Fine. Second is contention window. The contention window in the amount of the time divided into the slots. Right? Our slot is divided into some times. A station that is ready to send chooses a random number of slots in its wait time. A number of slots in the window changes accordingly to the binary exponential backoff strategy. This means that it is set to the one slot of the first time and then doubles each time the station cannot detect the ideal channel after the IFS time. It is very similar to the peep resistance method, except that a random outcome defines the number of slots taken by the waiting station. One interesting point about the contention window is that the station needs to sense the channel after the each time slot. However, if the station finds the channel is busy, it does not restart the process. It just stops the timer and restarts when the channel is sensed as ideal. This gives the priority to the station with the longest waiting time. So we can say that in our contention window, in our CSMA, if the station finds the channel is busy, it does not restart the timer of the contention window. It stops the timer and restarts it when our channel becomes ideal. Next is third method, acknowledgement. With all these precautions, there still may be a collision resulting in the destroyed data. In addition, the data may be corrupted during the transmission. The positive acknowledgement and the timeout timer can help guarantee that the receiver has received the frame. Okay, so it is a 3 component of our CSMA CA protocol. So what is the procedure of our CSMA CA like our CSMA CD? It is a flowchart of our CSMA CA. Note that the channel needs to be sensed before and after the IFS. The channels also needs to be sensed during the contestant time. For each time slot of the contestant window, the channel is sensed. If it is found ideal, the timer continues, and if the channel is found busy, the timer stops and continues after the timer becomes ideal again. Okay. It is a flowchart of our CSMA CA. Let's compare our CSMA CA with wireless network. Our CSMA CA was mostly intended for the use in the wireless network. The procedure described above here is, however, not sophisticated enough to handle some particular issues related to the wireless networks, such as hidden terminals or exposed terminals. We will see how this issue can be solved by then augmenting the above protocol with an handshaking features. The use of the CSMA CA in the wireless network will be discussed in the further chapters. So we conclude our session over here. So let's revise our discussion. In our first, we have discussed CSMA CA, carrier sense multiple access with a propagation time is equal to vulnerable time. We discussed 3 persistence method. First, non-NP over here. Secondly, we have discussed the carrier sense multiple access collision detection. We have discussed a particular scenario when both station send a frame, then a collision will occur and it detects the collision. We have discussed a minimum frame size. A particular procedure for our CSMA CD with a flowchart has been discussed. A 3-stage transmission, idealness and collision will be discussed in a CSMA CD. Lastly, we have discussed carrier sense multiple access with collision avoidance. We have discussed 3 methods for the same is the contention window, acknowledgement and interframe time. So it is an interframe space, contention window. It is a flowchart for our CSMA CA. So it is a question for you. Write down in your notebook and send back it to me as per the given direction. Okay students, see you in the next session. Thank you.